Hi. As now you already know the theory of hypothesis testing, we will discuss problems on hypothesis testing that are more applied ones, so that have direct physical meaning, and problems that you meet in your real life if you are an engineer, a medical scientist, or sociologist, and so on. So, and our today's topic is a hypothesis on proportions or on probabilities. So there is actually different ways to describe the situation we deal with here. So either we can say that we have a proportion, a population proportion. So there is a population, like for example, all people who live in the country, in a given country, and we are interested in proportion of people who wear glasses, for example, or proportion of people who support some political party, or proportion of people that prefer to sit at home on weekends, and so on. So, and this is called population proportion. Or this can be not just applied not to people, but to some other objects, like we can say that our population is, for example, items produced by some factory, and so we are interested in proportion of defective items, for example. So in this case, our population are all items produced by this factory, and we are interested in proportion of defective ones. And so all these can be discussed in a little bit different terms. We can say that what we are interested in is not a proportion but a probability. So we can say that our experiment is to choose a person at random, and we are interested in probability that this person has glasses, that this person supports some political party, that this person prefers to spend weekends at home, and so on. Or we choose an item at random, and we are interested in probability that this item is a defective one. So a proportion, what we call population proportion, and what we call a probability of a random event is actually the same. And so sometimes we say that we are interested in some proportion here, sometimes we say that we are interested in probability. So let's start with the most simple situation, when we have just one single proportion or just one single probability. And so our observations in this case are a series of trials. So as we are interested in probability of some random event, then we repeat the experiment this event is based on many times. And so n is a number of trials. M is number of trials that ended with an event of interest, so number of successes. We can interpret this occurrence of our event of interest as a success. So, and P is unknown probability of success. So we can interpret what is happening in this case like a series of Bernoulli trials. And we know n, we know m, so we know number of trials, we know number of successes, and we don't know p, and we want to, and we have a hypothesis on the value of p. So we want to test a hypothesis that p is equal to some given value p0. So p0 is a numerical value. So this is not when we solve some particular problem, this p0 must be a number. So, and we are to choose one of the following alternative hypotheses as a pair to the null hypothesis we are testing. So it can be either P more than P0 or P less than P0 or P not equal to P0. As you remember, the null hypothesis must be a simple hypothesis, so only hypothesis with equality is an acceptable option for the null hypothesis, and hypotheses with inequalities are composite ones, and so that is why they can be only an alternative hypothesis in this problem. So after a pair of hypotheses, the null hypothesis and the alternative hypothesis are chosen, we are to introduce the test statistic. So the test statistic to test such a hypothesis is a random variable that is calculated according to the formula you can see now. So t is the test statistic, and t is equal to m minus n p0 divided by square root of n p0 1 minus p0. So as m is actually number of successes in a series of Bernoulli trials, then we can say that m is a random variable that follows a binomial distribution with parameters n and p. So according to the physical meaning of what is happening, we can say that m is a binomially distributed random variable. And as you remember, if we are dealing with a binomially distributed random variable and parameter n is big, so we can use normal distribution instead of binomial one. So we can treat our random variable as normally distributed according to the de Moivre-Laplace theorem. And so we do this here, and we say that if we standardize this random variable m, so if we subtract its expected value, that is np, and if we divide it by the square root of its variance, and variance is n times p times 1 minus p, so we will get a standard normal distribution, so normal with parameters 0 and 1. And so that is the thing that is stated here. So they say that if the null hypothesis is true, so if p is equal to p0, then t follows standard normal distribution. So if p0 is equal to the real unknown value of p, then we are subtracting actual expected value and we are dividing by the square root of actual variance, and so we will get standard normal distribution as the de Moivre-Laplace theorem tells us. So this is the test statistic, and then the next step is to understand the configuration of the critical region and acceptance region. So here you see that it depends on the alternative hypothesis. So if alternative hypothesis is with inequality sign, then we have two-tailed test, as they usually say. Two-tailed test means that critical region has two tails, the left one and the right one, or sometimes they say two-sided critical region. If alternative hypothesis is p greater than p0, then we have a right-tailed test. If the alternative hypothesis is p less than p0, then we have a left-tailed test. So how this can be understood? So how can we understand that that tail of a critical region depends on the alternative hypothesis in this way? So we are actually to understand how the test statistic changes when the null hypothesis becomes less and less true and the alternative one becomes more and more true. So this what I'm saying now is a little bit not so very accurate from strict mathematical point of view. So an expression can be either true or false, and it's not so very accurate to say so less true or more true, but you probably, I guess you understand what I'm just speaking about. So your null hypothesis is P equal to P0. So if this is not true, difference between P and P0 can be small or big. So there can be situation that actual value of P differs from P0 dramatically, or there can be a situation that difference is very little, so they are almost equal. So, and this is what I mean saying that the null hypothesis can be more true or less true. So more true means that they are not equal, but they are almost equal. Less true means that they are quite different, P and P0. And so when the null hypothesis becomes less and less true, and the alternative one becomes more and more true, so this inequality difference between two parts of inequality becomes more and more, greater and greater. So you should understand where the test statistic moves, where its value, the value of the test statistic, does it increase or decrease. So, and if you see that when the null hypothesis becomes less true and the alternative one becomes more true, the difference between parts of inequality becomes greater and greater. So if while this is happening, the value of the test statistic moves to the right, becomes greater, then you will have a right-tailed test. If you see that in this case the test statistic moves to the left, becomes less and less, you have a left-tailed test. So if you see that both options are possible, so that the test statistic can move both to the right and to the left, in case when the alternative hypothesis is quite true, so the difference, in case when the difference is high. So in this case, you will have a two-tailed test. So that is how we choose a configuration of the critical region and the acceptance region. Okay, so and the last step that we usually do when we are solving these problems, hypothesis testing problems, not manually, but using some computer program, so is to find the p-value. And so the p-value also depends on the alternative hypothesis. And to find the p-value, you are to know the CDF of the distribution that the test statistic has. So here we see that if HO is true, then the test statistic has a standard normal distribution. That is why to find the p-value, we need the CDF of the standard normal distribution, so this phi function, tabled function that you already know, that we used when dealing with normal distribution. So, and formulas are given. So for left-tailed test, you have that p is equal to phi of t. For a right-tailed test, p is equal to 1 minus phi of t. And for the two-tailed test, p is equal to minimum of two numbers. So 2 phi of t and 2 minus 2 phi of t. So you calculate both and you choose the minimal one. So that is how the hypothesis on a single proportion or a single probability can be tested. And now it's time for an example. A department of traffic police recorded all traffic accidents caused by drivers during the last month. And totally there were 637 such accidents. So accidents caused by drivers. And in 178 cases, the drivers were women. So total number of accidents caused by drivers was 637, and number of those caused by women were 178. So the question is, can we say that women drive more carefully, more accurate than men, if a proportion of women is 30% of all drivers? So can we say based on this data, on this information, that women drive more carefully than men if women are 30% of all drivers. Of all drivers, I mean not only of those who cause traffic accidents, but of all drivers. So, what do we see here? Here we see that there is a series of Bernoulli trials. So a trial is a traffic accident, and so a traffic accident caused by the driver, and so we look at the gender of the driver guilty, and so they can be either man or a woman. So, and we can say that, let us say that woman is a success, and so this is total number of trials in a series of Bernoulli trials, and this is number of successes. So M and N are given, and so what is the hypothesis we are going to test? So they ask, can we say that women drive more carefully than men? What does it mean? It means that share of women among those drivers who cause traffic accident is lower than share of women among all the drivers. So we know that 30% of all drivers are women. So if less than 30% of those drivers who cause traffic accidents are women, this would mean that women drive more carefully, more accurate. And what is this share of women among the drivers who cause traffic accidents? So this is the same as probability of success in our series of trials. So we can say that our trial is when we look at the gender of the driver who caused the accident, and so probability that this driver is a woman and share of women among all the drivers that cause traffic accidents are actually the same things. So we can say that P is a probability that random driver who caused an accident is a woman. And so the hypothesis we are asked to test is that P is less than 0.3. So the probability that a random driver who caused an accident is a woman is less than 0.3. That means that share of women among those drivers who cause traffic accidents is less than 30%, less than their share among all the drivers. So, but we see that this hypothesis is a composite one. So that hypothesis we are asked to test is a composite hypothesis, so it cannot be accepted as as the null hypothesis, only as an alternative one. So we say that the hypothesis we are asked to test, that P is less than 0.3, is an alternative one, and so the null hypothesis is the same but with equality. So, and in physical meaning of the null hypothesis is that men and women drive so equally carefully, so that women drive as carefully as men, not less and not more. So, okay, this is our pair of hypotheses to test, and so the next step is to introduce and to calculate the test statistic. So we say that the test statistic is m minus n times p0 divided by square root of n times p0 times 1 minus p0. So m and n are given, and p0 is 0.3. p0 is the value we see here in our hypothesis. So this is 178 minus 637 times 0.3 divided by square root of 637 times 0.3 times 0.7. And so if we do all necessary calculations, we'll get that this value is minus 1.13 approximately. So then we can compare this. So we are to construct the critical and acceptance regions. So here we say that as we have less sign in alternative hypothesis, then we have left-tailed critical region. So left-tailed critical region. So critical region, acceptance region. And we don't know yet the alpha, the significance level, so they didn't give us alpha. That is why we are to choose alpha ourselves. And so let's choose the default value, 0.05. So if you have no ideas why alpha should be less or more than 0.05, then you take alpha equal to this value. So then here we have the quantile of the level alpha of the standard normal distribution, as we say that under null hypothesis, our test statistic follow follows standard normal distribution. So the quantile is the actually not t, it's better to use letter z as our standard notation for the quantiles of the standard normal distribution. So quantile of the level 0.05, that is equal to minus 1.65. So, and the observed value of the test statistic is minus 1.13. So this is our t is equal to minus 1.13. So we see that the test statistic is in acceptance region. So that is why we fail to reject the null hypothesis. So the null hypothesis is accepted. So t belongs to the acceptance region. Then that is why we fail to reject HO. So HO is accepted. So HO is that women and men drive equally carefully. So we do not accept the hypothesis we were asked to test initially. The alternative one, we accept the null hypothesis, not the alternative. So the answer to the question we were asked is no. So can we say that women drive more carefully than men based on this data? Our answer is no, we cannot at the significance level of 0.05. This is very important to state the significance level also. So the answer is no, we can't at the significance level 0.05. So that is how we can give an answer in the problem of hypothesis testing when we are asked to test a hypothesis on a population proportion or on probability of a random event that is the same. So what we can also do, we can also find the p-value. So as we have a left-tailed critical region, then p-value is just phi of t. So phi of minus 1.13. And so if we look for this value in the table of values of the phi function, we will find that this is approximately 0.18. So this means that this hypothesis will be accepted at any significance level less than 0.18. So not only at the significance level 0.05, but also at significance level of 0.08, of 0.1, of 0.15, at all significance level less than this one. So this is another way to give an answer. So you give an answer in form of the p-value, and then you choose your significance level and compare it with the p-value. So if your significance level is less than p-value, then HO is accepted. If vice versa, your significance level is more than p-value, the HO is rejected.